Am I audible?
Yes, yes, sir.
Can I start, sir?
Yes.
Okay. Good morning, everyone. It gives me immense pleasure to introduce Professor Raghunath Sahu, one of the distinguished researchers in the field of high energy physics. He is currently working as an associate professor at Indian Institute of Technology, Indore. He has also worked as a visiting professor at IIM Indore. After the completion of his Ph.D. in experimental high energy physics from Institute of Physics Bhubaneswar, he worked as a research scientist at University of Cape Town, South Africa, along with the visiting scientist at Institute of Physics Bhubaneswar. He was awarded with CNRS postdoctoral fellowship at Sabatec, Nantes, France, INFN fellowship at INFN, Padova, Italy, and has been a fellow of Institute of Physics UK. Professor Sahu has been associated with many international collaborations like Star Experiment at RHIC, Brookhaven National Laboratory, USA, and ALICE at CERN, Geneva. The prime research interest of Professor Sahu is around the study of global properties of quark-gluon plasma created in the Big Bang experiment, exploration of QCD phase diagram and search for critical point, exploring the properties of matter formed at high baryon densities. This is also the part of CRAPE-3 experiment, which is designed to study cosmic rays with an array of air shower detectors and a large area muon detector. He is also working on the applications of machine learning and artificial intelligence in high energy physics. Presently, Professor Sahu is a member of multiple professional bodies. Also, he is an editor, reviewer of many international journals and projects. Now I request Professor Raghunath Sahu to kindly deliver his talk. We welcome you, sir.
Thank you for the nice introduction, and good morning to all the participants from India. And yeah, so if I can share my screen. Okay, so you can see my screen now.
Oh, yes, sir.
Yes.
Okay, so I'm going full screen and use a pointer. Okay, so you can hear me well, and also you can see my full screen, right?
Yes, sir. It is visible and
Yes, sir.
So I request all the participants to mute from your side, because you see, so since it is my first lecture, so what I am going to cover is more or less uh, bits and pieces are taught in the earlier classes, because I also attended both of the classes earlier, just to know that how I can make a free flow, smooth flow to what I am going to discuss. And whatever questions coming, so you can actually write in the chat box, or wait till I finish my lecture. So this is just to maintain a continuity, and most of the things what I am going. So with these words, let me start. Assuming that you know all the probability distributions, both discrete and continuous, which are used for statistical techniques in data analysis. With that, so slowly I will migrate to data reduction and error analysis, and you can reach me on this email anytime you like. Okay. And before I proceed, so let me put a word of caution, because I believe this talk is recorded, and this will be put in different public media. So let me put some words of caution that these materials in this series of lectures are only meant for academic training, and this bears no commercial purpose. Okay, so we are a part of the teaching and learning process for the training of the next generation only. And we have followed many textbooks, internet materials, for which putting a proper reference is not always possible, and sometimes it is missed. And many materials thereof could be found just by googling. Okay, so essentially putting in a flow like a syllabus is more important, and explaining with examples. but most of the things nowadays could be found just by googling it. Okay, so with this let me start. The study materials I have followed, it is specific to different sections. For example, in my next lecture I will follow different books. Okay, so for this particular lecture I have followed the introduction to error analysis, the study of uncertainties, physical measurements by John Taylor. So this is a beautiful book. Okay, so anybody who is a beginner to learn about error analysis, so you can have a look at John Taylor, and his way of writing is beautiful. So I suggest you can have a look at this book. And little advanced is data reduction and error analysis for physical sciences by Babington and Robinson. And the other book having examples from physics is Practical Physics by Squeeries. So this also you can have a look, and all combination will give you a proper flavor of data analysis, error, and physics practicals. Okay, yeah. So the objective of this course is to deal with errors or uncertainties. So let me put the statement that no measurement is perfect, accurate, or exact, because this is a measurement. There are always instrumental, physical, and human limitations. So we understand any experimentalist at least doing experiment up to the level of intermediate. So we understand there are limitations coming from instrumental, physical, or human errors. Okay. So what is then the true value of a measured quantity? So the value one would obtain if somehow the errors in the procedure and the instruments are eliminated. So that will be the true value. So then the question is, one can improve the measurement processes but cannot eliminate the errors. Okay, so essentially we can constrain our errors or uncertainties by improving instrumental or procedural problems. Okay, and certainly we cannot get rid of the errors, and without errors experimental measurements are not complete. So you have to understand this. So we want to quote the best possible value for a measured quantity for any experiment together with its probable reliability. Okay, so I'll discuss about reliability and all that. Okay, so by quoting errors, we only tell how much the measured value is likely to deviate from the true value. Okay, and our estimation of error on a measured value is not a guess. Okay, and it is based on physical analysis of the measurement process, mathematical analysis of the related equations that apply to the instrument. Okay, so this will be clear once we go to the derived quantities in experiments which depend on some set of basic measurements. Then we propagate the errors using the mathematical formula to have the final uncertainty of the error. So I will use the terms error and uncertainty interchangeably, so don't get confused with error and uncertainty. So all are equal. And uncertainty in the data used to obtain the results. Okay, so once I enter into some problems and examples, so these things will be clear, but let's keep in mind that errors are not pure guesses. They can enter through physical analysis, mathematical analysis, and uncertainty on the data. And without knowing the size of errors, a measurement is of little use. Okay, so any measurement if you quote in your research paper or in the laboratory without quoting error, simply it has no value. So if a student attending the course may ask, am I going to get some mark if there is no error? It depends upon the evaluator, because if one experimentalist is looking into it, you have not quoted the errors, you have not understood the experiment. Okay, getting mark or not getting mark is a different ball game. But if you have not quoted the errors on your measurement, essentially you have not understood the experiment. So that will be the evaluation. So errors can be of two different types. One is determinate error, another is indeterminate error. What is determinate error? Can we have this can have the same sign and the same value in every measurement. So you repeat your measurement. So this determinate errors will have same sign and same value. So now you can guess that these may come due to procedural biases using a wrong scale. So you are using the same scale for all repeated measurements. So it is a procedural bias, and because of that reason, whatever error has entered into the measurement, that will stay with the similar sign and same value. And a wrong value of calibration constant. For example, you know all the instruments will be calibrated, okay, and because of the calibration constant, there can be also some error, but that we can determine. Its sign and value can be determined, and sometimes using wrong units. For example, if you see in high energy physics, people use natural units, and we are in natural units, H cross and C are taken as 1. And as you know, we are more accustomed with, although we started with different units from British time, like imperial unit, then we migrated to CGS unit and then SI unit. So SI unit is more standard and more abundantly used in general physical practices. But if you go to high energy physics where we are working, or the workshop is mainly intended for, so we use natural unit. So this conversion of unit sometimes could create a problem because we are not very much accustomed with, and that may introduce some kind of unit errors, which is also one can determine. So this falls in the category of errors which can be determined properly. So careful calibration of the equipment through repeated measurements can help us to get rid of these procedural biases. There are errors which fall in the category of indeterminate errors. So there is no way to know the size and sign of the errors. So every measurement yields a new value, and the origins are sometimes operator errors, some kind of biases, fluctuating environment, as well as experimental conditions and equipment reliability. Okay, so these errors are indeterminate, and that can enter into your process of measurement, and their effects can be reduced by averaging over many measurements. If you repeat your measurement and have a sample of measurements from which you get or estimate your average or mean value or the spread, so then you will give a better estimate of the quantity you are looking for. For example, when we first measured acceleration due to gravity in the laboratory, I guess all of you recall that at least your laboratory assistant or the teacher might have told you that you should take minimum 10 measurements. So that time we followed taking 10 measurements without understanding why 10, why not 15. Okay, so that 10 was an optimized number because after one measurement you may say my experiment is done. So without explaining the importance of statistics, I guess your laboratory instructor might have told you just take 10 measurements and take the average, and I do not know if you really dealt with the errors during that time. Okay, so let me little bit discuss about error, accuracy and precision. Most of you may be knowing, but this kind of workshops, it is better to remind and then going to little higher stuff. So error is an estimate of a probable difference between the measured quantity and the true value. Sometimes true value is known, sometimes it may not be known. So if we have some idea of the true value, then the measured quantity, the difference will give me what is the error. So if you look at this cartoon or the plot, so what I have plotted here is the probability density in the y-axis is plotted as a function of the value. I am not saying it is true value, it is the value of the measurement. And let's say with your repeated measurement, this follows a Gaussian kind of distribution, and I am going to explain you why Gaussian. So hold on with this. And if this is the situation, and the reference value or the true value lies here, and the mean value of your repeated measurements stays here, the difference between the reference value and the measured value, mean value of the measurement, is essentially tells me about the accuracy of the measurement. Okay, how accurate is your measurement will be determined from the reference value minus the mean value of your repeated measurement. So I guess accuracy of the measurement is clear now, and as the next generation instructors or next generation scientists, we can train our students in the laboratories and the classes so that the proper message goes to the next generation. Okay, so at least the accuracy, precision, errors, we should have a complete understanding. So if you look at the precision of the measurement, the precision lies in the spread. Okay, so the spread of the measurement, because we have repeated our measurement, this will tell us how precise our measurement is. So less spread meaning more precise. Okay, so resolution should be higher and higher. So if you see, I have not given you the true value here. So if the true value is somewhere around 2 or 1.98, so this measurement can be accurate, but if you compare the precision of this one versus this one, you will find this one is particularly more precise because the spread is less compared to this number. Okay, so I guess the message of accuracy and precision is clear, and with that, so let me define what is random error. So random errors are inherent in the reproducibility of the measurements performed during an experiment. So this may be reduced in principle, okay, not always, to a very low value by carefully designing the experiment, by careful techniques used for the data analysis, and making mean of the repeated measurements. So repeated measurements are actually very important. So random errors, they come from instrumental uncertainties and can be reduced by more reliable and more precise measurements. But those coming from statistical fluctuations can only be reduced by repeated measurements. So repeating measurements, as I told you earlier also, in our childhood we followed repeating the measurement, and possibly we will get the essence how an underlying principle or mathematical principle deals with the message of repeating the measurement. So in a counting experiment, we count longer, taking more and more events, meaning building statistics. Okay, so we have seen this, right? In the GM counter experiment or any nuclear physics experiment we do in the laboratory, we have actually waited longer. Waited longer meaning building up the statistics through the low flux. Okay, and we cannot reduce the statistical errors below a certain limit, and there is also no point going below a certain limit. So you may ask how long I will go on reducing my error or taking my counts. And if you are little cautious about your systematic errors, which I am going to discuss, if I have certain systematic errors, if I go on reducing my statistical errors below that, there is no meaning, because what I am going to do at the end of the day is to show either systematic or statistical error differently, or sometimes people also for theoretical purposes comparing with some model predictions, they take the quadratic sum of systematic and statistical errors, or they also choose the higher error. So if systematic error is higher than the statistical error, there is no point going on building up statistics. Okay, and the limits imposed by statistical errors are important. So for an experiment, so better I should redesign or design the experiment in a way my systematic errors are limited. For example, if I give you a practical example, so to reduce the systematic errors on different kind of measurements at the Large Hadron Collider where I am working now, so this is going for upgrade program, and next February we are going to take around 3 data, and by this we have upgraded many detectors, thereby reducing the material budget. So where background to my signal will be less, and by that actually I can reduce my systematic errors. So systematic errors are inherent due to some bias in the measurements performed during an experiment. and it is not reduced by repeated measurements. If you go on building statistics, your systematic errors will not get reduced. And what is systematic error? I am going to introduce with some examples. And sometimes it is also difficult to access the systematic errors, so they can be minimized only. So how they can be minimized? So you can carefully design, or the choice of experiment can be like that, and your technique should be different or sophisticated. For example, to deal with parallax elimination, calibration and all that. So in a simpler way of tabletop experiment. But if you go to collider or fixed target experiments in high energy nuclear physics or particle physics, so things will be completely different, and I will give one example of that. So for example, in our tabletop experiments, a wrong meter scale introduces a given amount of systematic error. So I can actually calibrate my scale to have a better measurement on this. And sometimes backlash in a rotary knob also introduces systematic error. These are small examples only. So often we apply cuts on parameters of a data sample which generates a clean sample of reliable data with reasonable errors. Because these cuts, when I clean up my data, when I apply some sort of phase space cut, or some cut means either lower threshold or higher threshold depending upon some physics arguments. So that cleans up the data but introduces a person based or the user based systematic error. As you can understand, if I am putting some lower value of transverse momentum cutoff, for example in high energy physics, so that becomes a user specific, and you know at the end of the day physics should not be user specific. My measurement, your measurement, and there is also something called universal measurement. Okay, so the universal measurement is something we should follow, and within systematic errors or statistical error, all individual measurements should agree. Otherwise, we cannot say that is one universal measurement. Okay, so it should be independent of the phase space cut we are using. Sometimes we estimate the background, which is often model dependent, because background in the signal extraction in high energy physics is something very sophisticated stuff, and it is not controlled completely, so we have to rely on some kind of model sometimes. I will explain that. So that introduces some sort of systematic errors. Let me give an example. So K star is a resonance. If I reconstruct in the proton-proton collision at the LHC in the channel of K to pi through the invariant mass reconstruction like this. Okay, so I am not discussing about nitty-gritty of the things. I am trying to bring a flavor of systematic errors. Okay, and here, so Bright-Wigner plus a residual background, which is a polynomial kind of background, is used to fit and extract the signal. So as you can see here, if I just look into the invariant mass reconstruction in the K-pi channel, so I will get a signal which is very tiny, but there may be, background coming from unlike pairs, and for that I have to deal with the mixed event background, and with the mixed event background which goes like this, if I subtract it, so then I will have a signal which is more visible here. But again, there can be residual backgrounds, and to deal with residual backgrounds, so this shape of the background here is taken as a polynomial background, but if you go to different PT, different range of the measurements, your background shape will be different, because at low PT, low momentum measurements, you will have different backgrounds coming from material budget. So particle interaction with material will dominate, or resonance decays will dominate your low PT part, and background shape will be different. So if I assume, for example, a residual background with a Bright-Wigner signal extraction, so this assumption of residual background is user dependent sometimes. Either I visually see, or a model, theoretical model tells me, guides me that my background could be a polynomial background. So as I explained to you, this may depend upon the PT range I am talking about. So in that way, my measurement will be affected by the kind of background function I am taking here. Just to give you a flavor how high energy physicists or nuclear physicists deal with systematic errors which are huge or sources are large in number. So the Gaussian is, again, you don't get panic because it takes, you may ask why high energy physics paper, a single experimental paper coming out takes almost from 1 year to 3 years, okay, whereas a theoretical or model based papers can be written in a month time. The reason being, we deal with different huge amount of data, and the amount of efforts we put into the typical analysis, for example, the analysis I gave now. So there are many different kinds of systematic errors. So somebody may choose a different fitting range, okay. So I can look into different fitting range and the impact. So normalization range can also be different. Sometimes the residual background, somebody may take polynomial 1, polynomial 2, polynomial 3. So that will also affect my analysis. So free width or fixed width, depending upon I am analyzing PP data or heavy ion data. So what guides me in the fitting procedure, should I fix the width or I make the width free to understand any medium effect? So bin counting or functional integration. So when you look for the number of K stars in your PT range, so to get the number, are you going for bin counting, which is discrete, or you integrate the function from certain range within some range? Are you using a relativistic Bright-Wigner function or non-relativistic Bright-Wigner function? And for the PID, when you are dealing with K1 and Pi1, so your N sigma cut, how clean it is, have you applied 1.5 sigma, 2.5 sigma or 3 sigma cut? What is your material budget and your hadronic interactions, your tracking efficiency? So many things will come into the estimation contributing towards the systematic error. And believe me, each systematic error source is studied as a function of the transverse momentum, as you can see. So there is a dependency on the PT, and the fractional errors are calculated. So finally the fractional errors will be summed up following some sort of error propagation formula to give you the total systematic error which will go in the final expression. And I am going to discuss about how the errors are getting propagated. This is just to give you a flavor of the systematic errors coming in to a typical analysis of resonance studies in high energy physics. Although you know a little bit, let me just refresh your mind here. Statistics, sample and parent distributions. Using repeated measurements, one generates a distribution of the data points, and the error will then correspond to the spread of the distribution. We know this now. So we try to understand the spread based on the predictions of a theoretical model. An inappropriate model can yield wrong results. Okay, so when I say parent distribution, it's essentially this may correspond to your theoretical model, like model telling you what kind of probability distribution function it should follow. So we want maximum information from the data without carrying out further repeated measurements. Okay, so we cannot go on measuring just to build up statistics or make the measurement better and better. We have to stop at one point of time, and when I stop, so I have a sample of data. It is not infinite amount of data available. So that sample of data, I would like to get the maximum information possible, and I would like to extract the best estimates of observable parameters and the effect of errors on them. And then I would also like to know the confidence level on the information obtained. So how confident I am, or what is my confidence level, so I can declare or claim my measurement. So this is where statistics comes into play, because I have a sample of data and there is something expected from the theoretical models, which I call as parent distributions. So since a sample distribution comes into picture, so now let me define what is my sample distribution. So for example, xj is a variable and j runs from 1 to n, and the x measured n times and when n is limited, so that is a small sample, and if n goes to infinity, the sample distribution should approach the parent distribution. That is what I claim. The most probable value, which is the mean, and the error on this as well as the spread in the data are to be determined from the parent distribution. Not possible if you have a small sample. Of course, you know that if you have a small sample of measurement, so you have its mean, which can be calculated using a mathematical formula, and you can also calculate the spread, sigma, of the sample. And if you want to compare with a large n limit with the parent distribution has a mean and also a spread. Okay, so these things we know, but we should keep in mind what is the difference between the sample mean and sigma versus the parent distribution mean and sigma, and they should agree with each other, or more or less within some sort of accuracy they should agree with each other when my n goes to infinite, meaning if I approach a large number of measurements. So we know the difference between one single value xj and the average results obtained from a sample of measurements or higher statistics x bar will give me the deviation. So xj is my single measurement. So from a sample of measurement I am getting x bar, which is the average. So the difference is delta xj. This gives me the deviation of my particular measurement from the set of measurements. So the actual difference between two values, irrespective of the reliability, will give me the difference, meaning the mean value differences. And what is my discrepancy? So if I compare my measurement to know the degree of discrepancy of my measurement with respect to some reliable measurement, let me call that y is my reliable measurement. So what is my discrepancy in the measurement? If my measurement is x minus y modulus, okay, divided by y, that means I am looking into the deviation of my measurement, absolute deviation of my measurement with respect to a more reliable measurement, which is y. So this also can give you the percentage of the discrepancy if I put one percentage mark. Okay, so the deviation with respect to more reliable measurement. Usually in out of practice or so, people do a mistake here. Mistake in the sense, my measurement x will be in the denominator because I do not care about the numerator, right? So because there is a modulus sign, x minus y is also equivalent to y minus x. So now the question is, should I put my measurement or the measurement with which I am making a comparison? So the answer is the more reliable measurement, your theoretical, model based or whatever, when compared to your own measurement, your reliable measurement has to be compared. Okay, and you know, if you interchange it, for example y with x, you are going to do a mistake. And I have seen in the laboratory measurements, particularly in my IIT also, sometimes when we rely on the TAs and TAs, particularly the beginner PhD students, if they have not understood this one properly, they do not distinguish x or y in the denominator. So that also creates a problem. So one has to be very careful, and it is our collective duty to educate everyone and go for the right measurement. Okay. So how do you calculate the mean of a sample distribution or sample of measurement? So I write this sample mean as x bar, and this is just adding up all the measurements and divide by the number of measurements you have done. Okay. And you can also know that the single measurement is not good as compared to a sample of measurements. So this we have seen in our laboratory, and we usually quote an extra significant figure for the mean to avoid rounding of errors. Okay, so this rounding of rule I will discuss maybe in my next class or so, because it is very important. And the reliability of individual readings and random errors only. And what about the deviation? So deviation, as I defined in my last slide, xi is my measurement, ith measurement, and x bar is calculated as the mean of the sample. So if you look into the deviation, randomly if I go on taking so many measurements, so my measurement can lie on the left side or right side of the mean, and if my right side is positive, left side is negative, so if I go on making the measurements, you can realize that they may cancel out, okay, plus deviation minus deviation, so they may cancel out giving you 0, and my mathematical formula tells me that yes, it is correct. If you look into the deviation from my mean value, so I may get 0, okay. So mean deviation gives no information about the spread or the reliability of the measurement.
Excuse me, sir.
Yes.
Excuse me, sir.
I just want to know.
Yeah, I just want to know that the value which you have shown in the slide x bar, is it a sample mean or the actual mean?
I defined it as a sample mean because xi are my measurements and I have performed n number of measurements. So that is why it is sample mean, and I am also talking about
in your sample the total number of units is capital N or small n? The total number of units in your sample is capital N or small n, because as you have shown in the previous slide that the total number of units is capital N. So I think it should be, either the total or the actual mean or the population mean, or otherwise I think here it should be small n, if I am not wrong.
It is a convention, so nothing to worry too much, because which slide I have shown small n?
Yes, in this slide.
This is capital. The sample distribution, my total number of measurement is capital N, and if I approach infinite number of measurements, so this should follow the parent distribution. That is what I told.
Okay, sir. Okay.
So I have used capital N.
Okay, fine, sir.
And if there is a typo and I am using small n, nothing to worry, because n I understand. So when I run over I and individual xi is my measurement, it doesn't matter. One can take small n, one can take capital N, doesn't matter. Okay, and it is a convention. So if you question why n, why not m, there is no answer, right? It is a convention.
Okay, sir. Fine.
Yeah, and most importantly, if you look at the deviation, as I explained you, and I look into the spread, so positive deviation, negative deviation with a large n limit can give me 0 or approximately 0. So the meaning I want to bring up here is the mean deviation gives no information about the spread because it will cancel out. Yeah, so this meaning should be clear, and then this will motivate me why I should define sigma as standard deviation or so, and why the definition type should be different. Okay. So the choice of the best value for repeated measurements. So now the mean square deviation or the variance, which is sigma square, is not 0. So this could give a quantitative estimate of the precision of the data. I showed you that deviation in general is invariably 0, or if you add up your positive deviation with negative deviation, this could give you 0. Okay, so in that case, if you think of, if I can take the square of the deviations the way it is done here, my positive square will be positive, negative square will be positive. So then the variance, the spread will be known exactly. So in that way, I go on defining the variance as sigma square, which is again, if n number of measurement is done, so I have to normalize it. Okay, so normalization comes from all sort of measurements, starting from classical to quantum mechanical and statistical, because n is user dependent. So I should not do something which becomes user dependent, keep in mind. Okay, so that is why normalization is very, very important. If you are dealing with n number of events, when you show your final measurement, this should be divided by n to normalize, to make even normalization. Similarly, in this statistical measurement, having a finite data sample, so I should divide by the total number n. So your total number n, capital or small, I usually do not care because it is user specific. If I understand it is the total number in the sample, full stop. So now, if you look at the dimensions of the variance, so this is with the dimension of x square, right? So although I could define the variance properly, I find that this variance has a dimension which is x square. So if I am measuring length, at the end I have to write the mean length, and the spread I am going to write as length square or centimeter square, which is not correct dimensionally. So now, since it is not dimensionally correct, I am going to define a standard deviation, which is sigma. It is not the variance, it is square root of the variance, and this is defined as root mean square deviation, RMS deviation. I just put one square root here, so now it has the dimension of x. Because you should keep in mind, when I have to give the best value, I have to write it is x plus minus sigma. Okay, so sigma should have the dimension of x. So that is the catchy point here. So that is the reason, rather instead of the variance to look into the spread of the distribution, I should use standard deviation or the RMS, which will give me the same dimension as of x. So I guess the message should be clear why I am using RMS or the standard deviation instead of using variance, which I started. So a particular measurement xi can now be thought of having a precision which is plus minus x, and there is a better than even chance that noise. Somebody speaking some question? No? Okay. So there is a better chance that xi will lie between plus minus sigma. Okay, because once we enter to Gaussian distribution and we know what is 1 sigma, 2 sigma and all that, so I should say that there is a better chance that my measurement will lie between plus minus sigma, because I am going to write it like, my final measurement is x plus minus sigma. So within 1 sigma I write as the spread, so that will designate my accuracy, how accurate is my measurement. Okay, so with this I can give you alternative formula of the variance also. So variance can be defined in this way, and if you mathematically expand it and simplify, you will find my sigma square is nothing but 1 over n, then sum over I, my number of measurement, then xi square minus x average square. So essentially this is square of the average, this is square of the average subtracted from the average of the squares. So it is like little tongue twisting kind of stuff, but you should keep in mind that if you look into the variance sigma square, it is essentially the square of the square of the average subtracted from the average of the squares. So once the mean x bar has been determined, this is the simplest way to evaluate the variance. So once you know the mean and you have a data sample, so you can do this thing easily in your tabletop experiment, and once x bar is known, the variance can be known. And this is quite often used for a finite data sample in your tabletop experiments to write the final number. For example, if I am measuring acceleration due to gravity, or using a slide calipers measuring some length, okay, or some radius, okay. So that time, so with repeated measurements, this formula for a finite data sample will be very much useful. Okay. So now slowly I go on introducing parent data sample, parent distribution. Okay. So standard deviation sigma of n measurements is not the best estimate of the standard deviation of a large number of samples, okay, which we might have obtained, and this n is limited, or my sample size is small, because maybe I could not wait for longer time, because everybody wants my number n should be larger, so that I approach the parent distribution. So we have chosen a mean x, which actually minimizes the sum of the squares of the deviations. So how this minimizes the sum of the squares of the deviations? Once I introduce maximum likelihood, I think I am going to discuss about that. So if the parent distribution has a mean which is mu, so now till now I have not brought in the parent distribution. So always I have dealt with the sample mean, sample spread and all that. So now let me bring the parent distribution into picture, and I define that my mean mu, okay, which is the first moment, is mu, and this is not equal to the sample average. Okay, so if this is the case, then the standard deviation of the larger set will be greater than the standard deviation of the sample set. So sample set is a small set of measurements, and the larger set is something, because I cannot really go like n is equal to infinite, which is unphysical. For a physicist, infinite is unphysical. So what I am saying is, I am dealing with a subset or a small sample for which x bar is my mean, and the parent distribution has mu as the mean. So if it is a larger data set, so the standard deviation will always be greater than the standard deviation of the sample set. So we understand this, and we have to always deal with a smaller data set. So what is the solution? Because this is the reality. Okay, I cannot eventually make measurement with n number of measurements present in the sample. My n will be finite. 10 million events, 5 million events, 1 billion events. Okay, it is a finite number. Okay, and theoretically my parent distribution is something where n usually, in principle, ideally should approach infinite. Okay, so what is the solution? The solution is any one measurement is determined by the remainder of the measurements, right, plus the mean, which is x bar, calculated from the finite data sample. So then there are only n minus 1 independent readings, right? If ideally, theoretically, n is my total number at which I should approach my parent distribution. So now, because I have made some measurement, so now I am left over with n minus 1 independent readings together with the mean x bar, which is calculated from your n number of sampling. So then the best estimate of the parent distribution is, instead of putting n here in the average, so this is good to put n minus 1. Although it looks a bit empirical, this will make sense. So because if you take, for example, spread for one data point, it should not be defined, right? I have only one data point. So then my n is equal to 1, so this will make me meaningless. So meaning, if I have one data point, I can talk about spread. Okay, in case of n here, I can talk about spread. So my general empirical formula with this argument now takes me to the domain that I should write while taking this average in the definition of sigma. It should be 1 over n minus 1, not n. And this makes sense to me, because although it looks empirical, with one number, one measurement, so this will give me no spread, or the spread has no meaning, and this is what I want. Okay?
Excuse me, sir.
Yeah, please go ahead.
Sir, since we are taking n tends to infinity, why are we not? Why can't we just put 1 by n? Why do we have to put 1 by n minus 1?
This is what I tried to explain you. You are saying that your n is infinite.
Yes, sir.
Practically, in a physical measurement, your n cannot be infinite. Okay.
Okay, sir.
So whatever sample you are taking, so the person y can come. Okay.
Okay,
Or I can actually build up more statistics, right?
Okay.
So then n will go to little higher value, and whatever number you are quoting from your measurement, n number measured x bar. So if I compare with my higher data sample where the spread is more, so then taking your sample as a subset of the total measurement, so I have x bar already given. So then I have n minus 1 number of independent measurements. So if I modify empirically, instead of 1 over n, I put 1 over n minus 1. So now, am I in a position to establish my formula, modified formula is correct? So that is what I am trying to explain you. So if I have somebody, so now let's say with this argument, this formula is correct. How do I justify it? So you have taken only one measurement. If one measurement is there, what is your n? N is 1.
1.
So now 1 minus 1, it is making 0. So essentially your spread or the standard deviation is unphysical. And that makes sense. If I have one sample, one data sample only, one measurement, there is no spread. And my earlier formula with n is equal to, with n without minus 1 was giving me some finite spread, right?
Yes, sir.
Which is meaningless. So that is the reason this formula bears more meaning with n minus 1 compared to n. And I guess 99% of the people in our laboratory experiments, we do not use the formula 1 over n minus 1, right?
Yes, sir.
So that is the reason I exactly know you asked this question. In a finite sampling, for example, if you are measuring, again I will go back to acceleration due to gravity measurement. When your teacher tells you, I don't know if you are a teacher already, but in general, when our teachers used to tell us, go for 10 measurements minimum, otherwise you cannot leave from the laboratory. Okay. So when I calculate the variance, usually I put n, not n minus 1. So in principle, you should put n minus 1. Okay. I think I have one example to show you. Okay. Let me proceed now.
Okay. Okay. Thank you, sir. Yes.
Yeah. And keep in mind why I have brought in, and if your student is asking you that, sir, by definition, or madam, by definition, it should be n, because that is what my sigma definition is. Why should I put n minus 1? So just give a flavor depending upon his or her level. If he is a PhD student, explain a little higher. If he is a MSc, BSc or below intermediate student, just tell that if you take a single data point, your spread by this formula is not defined, and he should be convinced. Okay. And if he is a PhD student or a faculty, then explain from the point of view I explained in my last slide. Okay, so if it is clear, so let me go to different kind of distributions, different kind of distributions pop in our statistical data analysis. So the shape and the mathematical form of the distribution depends on specific situation. For example, if I am tossing a coin, so my output is binary, right? Either it is head or it is tail. So this should follow a binomial distribution. For example, if I am dealing with a radioactive decay, where my average lifetime is known to me or it is expected. So this kind of distributions will follow Poissonian distribution. Any natural or resonance lifetimes, so I have to deal with Lorentzian distribution or Bright-Wigner distribution, okay, or Cauchy distribution, okay. So errors in repeated measurements. So errors in repeated measurements usually follow Gaussian or normal error distribution, okay, which is shown here. So the point of discussion here is, depending upon the physical process, the shape or the mathematical form of the parent distribution will be different. And I believe that these distributions, binomial, Poissonian, Lorentzian, Gaussian, so all these distributions should have been discussed in the last classes, and their limits, large n limits and all that, interconnections, those things might have been discussed. And certainly I am not going to discuss about those things, because the organizers have given me a different charge of discussing the least square technique, maximum likelihood and error analysis. So my discussion is limited to that. Otherwise, you should believe that the whole course is one semester course. Okay. The course which is taken up for this workshop is one semester, and we have to finish, I guess, in 6-7 lectures. Okay, so our duty is a bit tough, but I think you are cooperating with us nicely, and since the organizers have given us infinite time, infinite meaning is n going to infinity, which is unphysical, but that gives us a big sample in general, so we can go on discussing for longer period, because there is no immediate class or lecture. So that is a good thing. I should thank the organizers. So I as I told you, depending upon different physical processes, so your distribution types are different. And Gaussian is something which more or less we have to deal with while dealing with the errors in the measurement. And many of you may be thinking, why Gaussian if so many distribution functions are available, for example, Bayesian, binomial, Bright-Wigner and all that. So why Gaussian is so sacred? So I am going to discuss about that when I discuss in this class about central limit theorem. Okay, so I will bring up Gaussian distribution, but now since it is already introduced, let me remind you that the probability distribution function for Gaussian is written like this with sigma here. This is essentially a normalization, and you should keep in mind that it follows my xi minus xi bar weighted with the spread square. So you should just keep in mind more or less that it follows a deviation, and how much deviant it is, how much sigma deviant it is. Okay, and you will see in principle from our mathematical analysis we have seen the argument of exponent or log should be dimensionless, and my definition of sigma is also making a dimensionless here. So this is very, very important to judge that I am doing right or wrong. Okay, if somebody is taking sigma out of this square, it will be a mistake, and the way to know the mistake is the first day of physics learning, which is dimensional analysis. Okay, and little more about the properties of Gaussian is already known to you, so I should not spend more time on this, but I should remind you that this can be written in this way, and it is a normalized function. It can be normalized to 1. Okay, so that so this normalization factor can be determined, and if you are looking into the probability lying between a range, so the limit will go from A to B, which is the range. Okay, and we can associate a probability for a measurement to be mu minus n sigma mod from the mean just by calculating the area outside the region. Okay, so this will tell me the confidence limit. So how confident, when people quote that my discovery is 3 sigma versus 5 sigma, which Professor Kazari Majumdar discussed last time. Okay, essentially the simplest way of knowing is, so if I have a 3 sigma discovery, okay, so what is the chance that my measurement can lie outside this 3 sigma? So this is essentially 0.3%. Okay, so if I have 100 events which is giving me Higgs-like discovery, so if I have 3 sigma discovery, so then there is a chance that only 0.3 number of events can be unlikely to be Higgs type of events. Okay, so that is why when people talk about the 5 sigma discovery, 3 sigma discovery, so you should keep your mind, take your mind towards this probability of exceeding plus minus n sigma, which will give you a better flavor than just focusing on the integrated value. Okay, so these are discussed. So let me quickly, because I am already approaching 1 hour, your mind may be saturated because so much of mathematical expressions. So let me bring up maximum likelihood. So let us consider n randomly selected data points from an infinite set of observations. Okay, so again infinite is unphysical always. I don't have time to sit for infinite number, which is purely unphysical. So n is a finite number, but it's a large sample. So the probability of making any single observation xi will follow, for example, let me say that it follows a Gaussian distribution. And why Gaussian, I will explain from when I introduce in my next class the central limit theorem. Okay, so at the moment let me assume that my measurement xi follows a parent probability distribution which is Gaussian, and this Gaussian is characterized through xi, which is my measurement, and Gaussian is a 2-parameter function which is mu and sigma. Okay, and this Gaussian is known with mu and sigma, and mu is my first moment, sigma the spread is my second moment. Okay, and the third moment is called skewness, and fourth moment is called kurtosis. So these are used more often in more sophisticated measurements to look into criticality in the system. So if you look into the joint probability of making n number of measurements, so I will find that n or that finite number of measurement having possible mu prime as the mean will be the joint probability, which probability is multiplied. So if I multiply with this, so now my modified formula for the probability distribution will look like this. Okay, and at the end, to maximize the likelihood that my mu prime in the new measurement should be having greater probability to be my true mean of the distribution. So then what I do is this joint probability with respect to mu prime should be, the differential should be equated to 0. So now if you do that, so you will find that my mu prime after solving this equation is essentially equivalent to the true mean, and true mean is a mathematical formula which is sum over the measurements divided by total number of measurements. Okay, and I brought up this through Gaussian distribution and maximizing the probability. Okay, and when you have to maximize the probability, since it is a negative exponent, you have to minimize it, right? And this minimization procedure is called chi-square minimization, which Professor Majumdar discussed yesterday. Okay, because your chi-square also defined, in this way. This was your chi-square. So this chi-square minimization procedure follows the principle of maximum likelihood, right? So because if your single measurement follows a Gaussian distribution, your multiple measurement n number of measurements follows a multiplication of all the measurements following Gaussian distribution. And then what I did is, following the principle of maximum likelihood, how likely my new measurement with mu prime as the mean is closer to the true mean value. So I maximized this. So this is called the maximum likelihood method. So this has abundant use in my subsequent classes. Minimum. Okay, so far so good. I should put up some statements before I end this talk, and so after the end of the day, a little common sense will be good to deal with errors. When several independent errors are to be added, addition should be done in quadrature, which is much more realistic than simple addition. This I will explain you when I go for the error propagation formula. And if one error is less than 1/4 of another error in addition, then the smaller error may be realistically ignored, because you will see the consequence of that. So we should always focus on larger errors, not the smaller errors. And the experimental procedure should minimize the dominant errors. So you should design the experiment in a way your systematic errors are less. Your background coming from the material budget should be less. Okay. So your sophistication or sophisticated instruments will reduce the systematic errors. So this will implies that this must be identified and estimated using a pilot run before the final data taking. So if you are confused with what is pilot run, so now the LSC has finished its pilot run, and now we are analyzing the data with new detectors, so that we are ready with our understanding of the detector behavior when we go for the round 3 data taking at the end of February next year. Okay, so this pilot beam concept should be known to all the high energy physicists working in LHC at least, because LHC just finished pilot beam in October ending. Okay, we are analyzing the data for the pilot beam and try to bring the precision of each variable to a common level if possible. Okay, by repeated measurements. So these are some of the common sense I have written, which will be quite useful, and I guess my slides say that I should break here. Okay, if you have any questions, you can put up now. And
Excuse me, sir.
Yeah, please go ahead.
Sir, in methods of minimum chi-square or method of maximum likelihood or least square, sir, is there any way to tell that out of all these 3 methods, the value that I'll obtain will be the most precise value of my population parameter? Sir, is there any way to detect which will give the more precise value?
Yeah, so first thing is just to correct you when you say your chi-square minimization. Chi-square minimization follows the maximum likelihood method.
Okay,
Okay,
okay, sir. Okay,
because
sir.
both
Okay,
are
sir.
related. First
Okay,
thing,
sir.
okay? Because your definition of chi-square is here. Okay, if you minimize chi-square, it maximizes the probability, and that maximization of probability is maximum likelihood. Because I am looking for how close my mu prime is to the true mean, and true mean is calculated mathematically as 1 over n sigma I and xi. I am getting that. Okay.
Okay,
So
sir.
this is purely mathematical formula, and this adopts a probability maximization of the probability formula, and this is the maximum maximization, and chi-square minimization coming here because chi-square definition is here. Okay, so essentially we follow everything is same, and everything follows the maximum likelihood formula, and that is essentially maximizing the probability.
Okay, sir.
Okay,
So,
we all are in the same page of the
okay.
discussion, and the underlying principle is maximum likelihood.
So, sir, if we are taking least square method also, the more precise method is maximum likelihood. If we are comparing
That
least square,
that is the underlying principle. If I in my third lecture I will discuss about least square fitting procedure of the data. Okay, so there
okay, sir.
also I will use maximum likelihood method.
Okay, okay, sir. Thank you, sir.
You are most welcome.
Hello, sir.
Yeah.
Yeah, sir. In the, I guess in previous slide where you mentioned the thing about 1 by n or 1 by n minus 1.
Mm-hmm.
So if we take, as you mentioned, that we are taking large amount of data. Okay, so that's why we change this 1 by n to 1 by n minus 1.
Mm-hmm.
Okay, so, but does it matter that, let's say we have the data, 1 billion events. So does it matter that we subtract 1 from 1 billion? Does it matter? Then we are taking n to be large enough. So
Yeah.
I guess 1 by n and 1 by n minus 1 both are almost the same values.
I got your point. I got your point. So you are saying if n is equal to 1 billion, 1 million or so,
Yes,
so
sir.
minus 1 doesn't matter. I absolutely agree with you. Okay? Because in the denominator, if I put n is equal to n or n minus 1 with large n limit, it doesn't matter. Okay? But usually you have to also give respect to the people who are just taking 10 measurements in the laboratory. Agreed?
Okay.
So if you take 10 measurements, 20 measurements in the laboratory, this n will matter.
Yes,
Okay.
sir.
And I'll show you with my next class. I have a beautiful example. I'll just go on measuring the weight of eggs. I have a farm, poultry farm, and I'll just go on measuring the eggs. Okay. And with that example, I will convince you next time. You are measuring 20 eggs or 25 eggs versus 100 eggs, how the precision matters, how n comes to picture. So I will discuss about in my next class.
Excuse me,
Thank you,
sir.
sir.
Excuse me, sir.
Yeah.
If you please let me allow, then may I explain the reason that why we are taking here n minus 1? Actually, sir, uh, we are taking here 1 over n minus 1 because uh, as we have to substitute the unbiased estimate of the population variance. And if you see the statistical analysis, then you will find that if you substitute the sample variance at the place of the population variance, or if you have to estimate the population variance, and suppose you are taking the sample variance, that means if you use 1 by n, then it would not be an unbiased estimate. But if you substitute 1 over n minus 1, which is called the sample mean square, it will be an unbiased estimate of the population variance. That's why we always take 1 over n minus 1 for the small sample test. But for the large sample test, it is not compulsion. You may take 1 by n or 1 over n minus 1.
It actually doesn't matter. But you see, your formula, as you rightly explained, the logic is given here. And by putting n minus 1, it is an unbiased one, and that logic
Yeah,
is given here.
yeah,
And
yeah.
the
If you
large
substitute,
n, Yeah,
If we put here n, it would not be an unbiased estimate.
Yeah.
That's why we generally prefer 1 over n minus 1 for the small as well as for the large.
I explained this thing. I explained this thing clearly in this slide.
Okay.
And as both of you rightly pointed out, for large n, it doesn't matter. Because I divide 1000 or 999, it doesn't matter.
It doesn't matter. It doesn't matter. But for a small, but for a small value, it has some significant difference.
Yeah. For small number of measurements, that makes significant difference because it is a small set of samples. And in addition, empirically this is also correct because the formula should be checked first dimensionally. Second, with a reduction to what I know. So, for example, if I have one measurement only and I put n is equal to 1, so this is unphysical, and that makes sense to me. That makes sense to me because with one measurement that I cannot define a spread.
Yeah, you are right.
So that is the reason, once I have devised a formula, I check first dimensionally, second the physical or unphysicalness. And this modified formula agrees with large n limit, small n limit. So that is the point I made that I should use this formula. Okay. So any other questions? So yeah, please go ahead. Yeah, so next class will be a bit more mathematical because I guess this class I just refreshed our mind, redefined couple of things, introduced few things which are new. But next class will be more mathematical and new concepts will be introduced, and I urge that you take good lunch, take a 30 minutes nap so that your brain is reset, okay, and that will be just after your lunch. So take a cup of tea or coffee, and then we'll fly together.
Yeah, so the next talk will be at 3 p.m.
Yeah.
So I think we can close this session, and we will meet at 3 p.m. after the lunch.
Okay, sir.
Okay. Thank you so much.
Thank you, sir. Thank you very much.
Of sharing the screen so that at least I can check because I will migrate from PPT to Keynote.
Good afternoon, sir. Yeah.
Yeah. Good afternoon.
Let me see.
Yeah, I guess I got some. Correct.
Good afternoon, sir.
Good afternoon. This Microsoft team is a bit different compared to our Google Meet or Zoom, WebEx.
Yes, actually.
Even we cannot know who is there in the audience. So, but anyway, so you can see me and my full screen view of the keynote, right?
Not exactly full. The sidebar is coming actually in your PPT.
Yeah, so sidebar should be my video, right?
Okay. Yes. Also the small those PPTs actually 1, 2, 3.
No, but we can see Raghu also.
Yes.
Raghu cannot see us.
Yeah, I cannot see anything, only my. But my keynote is full screen, right?
Yes, that is okay.
Yeah, so it is slide 1, slide 2, yeah. Yeah, I just migrated from PPT to Keynote, so features will be different. No laser pointer, so no cursor. Okay, so please let me know when to start. So everything is fine in Jalandhar. You have started going to office without mask or no?
Yes, yes. Everything is fine here.
Without mask,
But
right?
the classes are still offline, yeah.
Yeah.
You are at CERN right now, no?
Yeah, I am at CERN and CERN is with mask now.
Okay. But I
Single
mean,
of,
there are more cases coming up recently.
in fact, compared to August, September, I think it went down and then now it is up.
Mm.
So that is why single office and a mask in the
Okay.
common area.
Yes, I think we can start now the next session, right? Yes.
Okay, so you are recording the session, right?
Yes, yes.
Yeah, maybe you can make a fresh start of the recording because we are our private conversations will not be there.
Okay.
Yeah.
It is also live on YouTube.
Oh, I see. Okay,
Yes.
so fine, fine. Anyway, so we
Yes.
talked on sense, but
Yes.
nonsense, not nonsense. Okay. Anyway, so fine. I think we have got to start slowly, and participants will join slowly. Fine. Welcome back to the session again on estimation of errors in statistical data analysis. If maybe I can start, and if there is any question, so we can come back to this afterwards. I think that will be better. Okay. Yeah. So in the second lecture, the content is the following, and I will start with why errors are Gaussian. I will show the rules for rounding off. Usually that is very primitive, but the point is we should get reminded of, because I also do similar kind of mistakes in rounding off till now, because it is not Delhi way of looking into. So we should not land up making a mistake in the laboratory particularly. So then we will discuss about weighted average, and I will bring forward the discussion of weighted average from the principle of maximum likelihood, so that
Sir,
yeah,
sir, sorry to disturb you. You are on slide number 1, right?
I am in slide number 2.
Sir, actually screen is not changing. It is showing that you are on slide number 1.
You cannot see the contents?
No, sir.
Yes, sir.
It's same here.
Then there is some problem. Okay. So what do I do?
Now, sir, it is changing. Yes. Now you are on slide number 2, contents.
No, but I should go to my play mode. Now you can see contents.
Yes, sir. Yes, sir.
Is my slide changing now?
No, sir.
What is this? So you cannot see the title of the slide, why errors are Gaussian?
No, sir. I can see slide number 2, contents.
There is some problem.
Sir, while you are presenting, you have to share your whole screen, not the particular.
Okay, so let me try again sharing. I don't know how to stop it. Let me try something. Okay. So if I go for sharing now, it should share everything, right? My screen 1.
Yes, sir, whole screen.
Okay. So I did the whole screen now. So can you see my slide number 1 now?
Yes, sir.
Yes, sir.
Let me change the slide and counter check.
Yes, sir. Now it's
Yes,
okay.
sir. It is working.
Okay.
Now it's
That means you have to share the whole desktop. Perfectly.
yes, sir. Actually, in presentation mode, there is another window comes up, so we can't see.
Okay. So now it is fine. I can change my slide and you can see in the play mode.
Yes, sir.
Okay, perfectly. So, perfectly all right. Let's go ahead. So, the content is the following. So, I am going to discuss why errors are Gaussian. Unfortunately, in the keynote, I cannot use a cursor or laser pointer, but I have put it in a animation mode, so there will be no problem in discussing. So, then we will discuss about rules of rounding up and weighted average. I will bring the discussions forward from our knowledge of principle of maximum likelihood. Then we'll discuss a little bit about the rejection of data, which anomalous data should be rejected. What is there a rule for that? Then we discuss about propagation of errors, square root rule for counting experiments, the null experiment and setting confidence limit, which will be really required for looking into events which are actually events or the phenomena which are not seen in the laboratory, or like beyond standard model physics, which is not observed but we expect it to be observed. So those kind of phenomena. Then to the advanced learners, I should not stop at that point. The advanced learners, I should introduce error ellipse, error matrix, and the transformation of errors. This will be a little advanced part, but I think as a matter of completeness, I should introduce that. Okay. So before I start, let me make a statement here. The statement is the following: a single death is a tragedy, because single death happening to the relatives, it is a tragedy. But in the corona age, it is needless to explain that a million deaths is a statistics. Okay. So this brings forward what is the necessity of dealing with statistics. Okay. So nowadays this worldometer for corona, and everybody must be watching the cumulative data, daily data and all that. So this has become a statistics, and this statement makes sense in the present time. So now let me migrate to why errors are Gaussian in nature. So this is a typical Gaussian distribution I have shown with the mean value mu and with different sigma values like mu plus sigma, mu 2 sigma and all that, and how much of area under the curve it covers if I talk about 1 sigma, 2 sigma and 3 sigma. So those things are discussed in Professor Majumdar's talk yesterday. And that physical measurements are associated with resolution or error. So in optics language, you can also talk about resolution, and in statistical language, we also talk about error. So we express a measured length, for example, as 12.3 plus minus 0.1 centimeter. This error is a Gaussian standard deviation. What I wrote here, 0.1 centimeter, is essentially a Gaussian standard deviation. So if you look at sources of error, what are the sources of error? Let's consider the measurement of this length which I talked about. And error can occur because of optical parallax. If I am using a ruler for measurement, ruler's calibration, rounding errors particularly I am going to discuss about, secking of the hands, etc. Secking of the hands means it is user dependent, right? So most of the optical instruments you might have realized in your laboratories, there are many problems related to parallax in optical bench and all that. So those are mostly user specific, and secking of a hand is also part of the user error. So in digital measurements, you may say that, okay, so now it is a digital age, let's migrate to digital instruments, but you cannot rule out electronic noise, which is sometimes called white noise, calibration of the device, and any other errors which we may not have foreseen. So the measurement imperfections occur because of many reasons. Some reasons are understood, some reasons may not be understood, but our aim is to understand our measurement and put up a confidence that, okay, my measurement is correct. It's a discrepancy from the non-theorized or theoretical prediction and all that. So this behavior of a variable, which is a sum of several others, is dealt with a powerful theorem which is called central limit theorem. So now, to address the issue of why errors are Gaussian, let me introduce central limit theorem. So the references I talked about in my first lecture, essentially I migrate to another book here because of usefulness of the contents. So this particular section I am using from Statistics by Roger Barlow. So let me talk about the central limit theorem now. So as for the central limit theorem, if you take the sum capital X of n independent variables, xi's, remember these are independent variables, mostly we'll encounter mostly in independent variables. But in specific experiments, we may also find, depending upon the physical system, your variables can be correlated. So we'll take up that discussion separately. So each taken from distribution of mean mu I and variance vi or sigma I square. The distribution for capital X has an expectation which is sum over of mu I, and it has a variance Vx which is sum over of the variances Vi or sigma I square, and this distribution becomes a Gaussian in the limit of n tending to infinite. So now the way I would like to proceed is I will show you a mathematical proof of this central limit theorem for the first 2 points, and the third point, since it is difficult and needs a different kind of mathematical jugglery. So what I will do is I will prove you in an empirical way, showing you some example. So with this, let me go ahead. Gaussian, as you know, is an important distribution, a quantity produced by the cumulative effect of many variables, like the one I told about addition contributing to capital X, will be a Gaussian almost approximately, no matter what the distribution of the original variables might be. So you keep in mind, my xi's, they might follow individually different probability density distribution, but when you talk about the cumulative effect of many variables, that will follow a Gaussian, irrespective of the original distribution function followed by the individual measurements. So that actually makes Gaussian distribution a very important distribution, or more or less, the naturally occurring phenomena. I think naturally occurring phenomena saying will be a little odd. So let me say that, it is an important distribution. So CLT, central limit theorem, works better at the center of the distribution, because when I say it approaches a Gaussian distribution, and you have also seen that almost 99% of the distribution is covered by 3 sigma. So I would like to stick towards the center of the distribution, and I will try to ignore the tails which has less contribution, tail or wing, whatever you say, depending upon your analysis. So let me go ahead in proving the central limit theorem. So the first point is this capital X, which is coming from the sum of the individual measurements, repeated measurements. So the expectation of the sum of expectation values. Okay. So now I write my capital X as sum over Ixi, and once I take the expectation values, so I can show that this is nothing but sum over of mu I. Perfectly alright. Okay. Similarly, I can also prove my Vx, which is sum over Vi, the variances. So this is sum over sigma I square, and it is purely mathematically one can show. If I go to V capital X, the definition of variance of capital X is X minus X average square, and you take the square of that, and once you take the average, so you can actually expand this, and I guess you can follow the derivation, mathematical derivation here. And what is important towards the end is the last term is a covariance term, and this is equal to 0 for independent variables. Okay, since my measurements are independent, so your xi and xj will be independent, so that will make your second term 0. So once second term is 0, so our second point is proved, because your sum over I xi minus mu I square average is essentially sum over of sigma I square, because that is the definition of sigma I. Okay, so first 2 points are proved. So now to prove the third point, that n tending to infinity, this capital X probability distribution function should actually approach a Gaussian distribution. Keep in mind approximately, or it approaches the Gaussian distribution. So now let me show one histogram. So how I am getting this histogram, as I told you, since mathematical involvement will be little higher level and we have general audience. So what I have taken is, I will prove this by taking one example. Okay. So This figure A shows a histogram of 5,000 numbers taken at random from a uniform distribution between 0 to 1. And you can see, without going to the details of this, you can see it is certainly not a Gaussian, because you can generate random numbers. I think Professor Arun Naik will teach you about that. So once you have random numbers generated from 0 to 1, if you fill in a histogram, you will find this is this more or less with statistical fluctuations. This is a flat distribution. It is certainly not a Gaussian distribution. So next step, what I am doing is, again I am taking the same number 5,000, and each the sum of the pair of random numbers I am combining. Okay, what I am plotting now is I have added x1 with x2, and that becomes my x. So similar thing, and now I am making it my capital S and filling it in the histogram. So slowly the distribution will look like a triangular distribution. It is not a flat distribution now. So this actually you can do it when random number is introduced. You can play with this. And if you go on doing this, if three uniformly distributed random numbers will be added together, so again you will find this is approaching, towards flatness to triangular, and again it becomes little curved and all that. And now let me add 12 uniformly distributed random number from 0 to 1. So 12 addition, if I put it in a histogram, so what I find is slowly that is going towards a Gaussian distribution. And this exactly brings up the example and giving us the fact that once your n number goes on increasing, your flat distribution, which is the origin, we started from 0 to 1 uniform random number, so that makes my x distribution to be Gaussian. Okay, so this gives a flavor that if you go to large n limit, slowly your distribution is becoming a Gaussian, irrespective of the fact that where I started my individual entries taking from. Okay, for example, you might have seen my first plot A shows that I took the individual entries from a flat distribution. Okay, and same entries I am taking, but I am adding, let's say 2 first, then 3, then 12, and slowly I am emerging towards a Gaussian distribution. That is exactly as per the definition or as per the theorem, point number 3 I gave in my last slide. Okay, so I think it is consistent that in the large n limit, irrespective of the fact that individual measurements can follow different distributions, the capital X, which is getting the contribution from cumulative effect of all these individual measurements, that is going towards Gaussian distribution. So after CLT is introduced, so let me go to.
Excuse me, sir.
Yeah. Please go
Sir.
ahead.
Yes, sir. Sir, according to the central limit theorem, as n is increasing, are we saying that the summation of the random variable approaches normal distribution, or the summation of the mean and variance approaches normal distribution?
Summation of the variable xi, because
Variable.
what,
Okay, sir.
yeah,
Yes,
what I showed you is what I showed you here is I took the entries from the uniform random number. Okay, and I added, you can see in the point number B, actually keynote is not allowing a laser pointer. So you can see in the point number 2, my x is equal to x1 plus x2. Okay, so similarly I went on increasing this x1 plus x2 plus x3. So I went slowly up to adding x12, and I saw that it is slowly emerging towards the Gaussian distribution.
Okay. Okay.
Okay.
Sir.
Yeah.
Yes, sir. Thank you, sir.
Yeah. So I welcome the small questions which will actually create a gap in the understanding. Small questions are welcomed, and detailed discussion if you have something, so we can defer to end of the talk. So this kind of small questions I welcome.
Sir.
Yeah.
Sir, in the previous the graphs, I was seeing that the x values were increasing a bit.
X values increasing. Yeah, fine. So because I am adding it. So once I created 0 to 1, so all are decimal points, and once I go on adding, so it is supposed to increase, right?
Yes, sir, got it.
Yeah, so that is expected. Good, good, nicely you have observed that. Fine. Okay, so let me go ahead because I have lots of material to cover. So fine. So if I look into repeated measurements, suppose the same quantity is measured many times. Let all mu I have the same value. So then I say that it is my mu. And all sigma i's, they have the same value. I say it is sigma. So then if I use the central limit theorem, I can prove that this expectation value of the x is sum over of mu, and since I have n number of measurements, so it is essentially n mu. And in terms of the average, so x average can be written as x divided by n. So x average is nothing but mu. So assuming the measurements are independent, the variance of x bar is the variance of x divided by n square. So why I am making n square? Because this has to be in the same unit. Square as v is a square quantity. So now the v is a square quantity. Keep in mind. So because of that, so it is sum over vi divided by n square. So this is sigma square by n. Let me try to understand what is my average of x bar, right? Because that is important to physically perceive. So what is the meaning of x bar average? So essentially it is average of the mu. So what do you mean by average of x? So if you spell it out, you will find that we have taken n measurements, x1, x2 up to xn, and we have averaged them, and that average is called x average. So essentially that is your sample average. This result is subjected to statistical fluctuations. So but on average, its value will be mu, sometimes more and sometimes less. So if your distribution function, I do not want to relate mu to your original distribution function, but if you repeat your measurement within the sample size also, you may find fluctuations within mu. Because I took 10 measurements, calculated x average. Again I took another 10 measurements, I got another x average. And I continued with, let's say, 100 such entries. I will find that this average is also fluctuating, and that average of x, if I take expectation value of that, so I will land up with mu. And this fluctuation is entering, it is only because of this limited number n. Otherwise, what is the source that I repeat my experiments 10 times and I will find my x average is different? Okay, and if I average out on the average, so I will find mu. So I may say that this x average fluctuates around mu, following a variation which is sigma square by n, and this dependence on n is expected because of the finite statistics. Okay, so in this way I tried to understand what is x average and what is the expectation value of x average. Now note that the standard deviation of this average falls like 1 over square root of n. And the statistical rule is averaging is good for you. The way I explained you in the previous slide, always averaging is better because that will take out the fluctuations. And I repeat the experiment 10 times. So I have x average, 10 entries of x average, and I take average of that to get a better value. And then better example is the law used in economics, the law of diminishing returns, or the principle of diminishing marginal productivity. So Google it and try to relate this law of economics to this repeated measurements and the standard deviation falling like 1 over root over n. So to get the meaning of this is the fall of the deviation like 1 over root over n is equivalent to the following statement. To get twice as good a resolution, you need 4 times as many measurements because it is falling like 1 over square root of n. So if you want that your resolution has to be better twice, 2 times, so you should take 4 times the measurement. For n independent measurements, the average has an expectation value which is exactly the desired quantity, and the variance falls like 1 over n. The resolution or the error on the average is sigma divided by square root of n. So this is smaller now by a factor. You see, usually your sigma was the resolution or the error. So now, because to take care of the statistics, you find that this is smaller by a factor of square root of n than the original error in the single measurement. So this holds for any kind of distribution. This is independent of the Gaussian distribution. So sigma over square root of n for any given sample. When I talk about the sample, I do not care what kind of probability distribution function that follows. So I can define the number n, the sigma, and I can calculate the average. And when I have to write what is my average value, so average value will have some statistical fluctuation or the error. So that is what I showed you while interpreting my average of the expectation value of x average. So the final number will have a error which is sigma by square root of n, and this is called the standard error on the mean in any given sample, irrespective of the probability distribution function that follows. How do I understand this? So now if you look at the right hand side plot I have shown here, so you will find for any sample, I have not talked about this Gaussian or Poissonian or anything. So for any sample, there is a sigma that's spread. And looking into your statistics, if you go on increasing the statistics, your resolution will be better because the error on the mean follows sigma over square root of n. Okay, so square root of n times your resolution will be better and better if you go on increasing the statistics. So this is what I talked about in this example, and now let me take a better example. So now what I am doing is, I am going to measure the weight of eggs produced by farmers' hens, and we found that the standard deviation of the measured weights are 10 gram. And he feeds a group of hens an expensive vitamin supplement, which will pay back its costs if it increases the weight by the factor by 2 grams. So instead of giving this vitamin, expensive vitamin, so the farmer decides to do experiment for, let's say, 20 eggs, and he calculates if weight of the egg is increased by 2 grams, so he will get the profit. Then he measures this 25 eggs from the vitamin fed hens, and the average is increased by 3 gram. So you see, the average is silent here. I am talking about sigma only. So now you see the average is increased by 3 grams. Now the question is, does this prove anything useful? So he was expecting 2 gram increase, and now the increase is 3 grams, and the sample size is 25. So with this, do you think, how do you statistically interpret this number and get a feeling of it? And certainly you are not going to experiment this expensive vitamins with all the hens available in the poultry farm, right? So here, statistics plays a big role. And although the farmer was expecting 2 gram increase, though now on the average there is increase of 3 gram, the answer to this problem is, it is not a substantial increase, because the standard error on the mean is 10, which is your standard deviation, divided by square root of 25, because square root of 25, because you have taken a sample size of 25. So that is not 2 gram. So error on the mean is 2 gram. So 2 gram compared to 2 grams, so now the average increase of 3 gram is nothing but 1.5 sigma increase. And 1.5 sigma increase is not taken as significant. So now at this point, if I increase the sample size slowly, Can I get a better result? Answer is yes. So farmer observed from only 25x, increase was 3 gram, and this is just a 1.5 sigma increase, which is not substantial. So now let's experiment on this, and let's now increase the sample size to 100. So what is the standard error on the mean? So this is again the spread 10 divided by square root of 100. This is 1 gram. And the increase of the average by 3 gram with respect to this standard error of 1 gram is now 3 sigma, and 3 sigma is significant. So from your pool of hens, instead of taking a small sample and interpreting, okay, I am getting average increase of 3, if I see the same thing with larger statistics, so this tells me that my increase is significant. I am getting a 3 sigma increase. So here statistics plays a role. What sample you take and then interpret, that matters a lot. Okay. And other dynamics we have not taken into account. For example, we have assumed that all hens are healthy and at the stage of giving eggs and all that. Okay. So otherwise, unless you take a similar sample, you cannot interpret the data. So that is why you see nowadays many people look into COVID data. You can very well know that COVID data is very sensitive because of multi-parameters involved. So interpretation of COVID data is actually very highly sensitive and is a different kind of game. So now I could show you that statistics plays a big role in bringing a physical message, and this is square root of n rule applies irrespective of the statistics, and it is very important while quoting the total number and interpreting the dynamics of the problem. So this problem,
the 2 gram has no significance in this problem, right?
can I repeat? I cannot get it.
The 2 gram mentioned in the problem has no significance.
No significance. 1.5 sigma is not very significant. Yes.
Okay, sir.
Yeah. So compared to 1.5 sigma, your 3 sigma takes you to 99%. So your significance increases. Okay. So I told you in the last class that how the interpretation goes. The interpretation goes in the following way. So if you cover 3 sigma, so your percentage will be 0.03 or so. So like out of your whole sample, you can interpret that your chance of failure is 0.03%. And if you take 1.5 sigma, so I have to calculate your 1 sigma was 68% or so. So then your chance of failure will be 100 minus that 68% or so, or 70%, whatever calculation will come from 1.5 sigma. So 3 sigma is significant and 1.5 sigma is not. Okay, because you have to always see the chance of failure, and chance of failure will come from how much sigma you stay out of your probability distribution. For example, 1 minus seeing that probability. So I discussed in the last one, taking the example of Higgs events. Okay, so now let me quickly, I think I'm going slow with time, but fine, I have one more class, so hopefully things will be covered, but let's go ahead. So let me put up the rules for rounding up. So although it looks very easy, but we have to keep few things in mind. Okay, so those things which should be kept in mind, that I will actually remind you. So the number of digits to be kept in numerical result is determined by errors or uncertainties on the result. So now when I talk about rounding up, you keep in mind you are making a measurement, and in the measurement you have some value of the result, then you are getting some error. Now your job is, how do I present these numbers? You may present in your scientific reporting in one of the journals, or in your laboratory notes, but there is a rule of presenting these numbers, and unfortunately we also find many people doing mistake. You go to archive and find some papers, people write the numbers in different tables without doing proper rounding up, and the rounding up is also having problems. As you can see in any calculation in the using calculator, so depending upon your resolution of the calculator, you may go up to 10 decimal points, 12 decimal points. Sometimes people write whatever they are getting 10 decimal points in the table in the scientific paper, which is absolutely wrong. Okay, I'll tell you why absolutely wrong. And people just take out after 3 digits, and whatever they are getting, they are writing it. So now the point is it so abrupt that it depends upon the people write the way they like? Answer is no. Okay. First thing you have to keep in mind, each instrument has a least count. So your quoting of error cannot go below the least count, right? I cannot measure something beyond the limit or the resolution of my instrument. So if that is seen from your table, so then a good experimentalist will give you 0. Because you have quoted a number which is not measurable given the instrument. First thing. Second thing, since we are using calculators everybody and 10 digits are coming, if I write 10 digits, it is a blunder, because sometimes I cannot go below my instrumental, why sometimes, always, I cannot go below my list count, full stop. So second point is, if I do the rounding off has a rule. How many digits to be kept? So first thing is, you have to look into the error or uncertainty. Uncertainties cannot be below the measured limit of the instrument. So this guides me how many digits I should put for the uncertainty or the error. Let me take one example. So in the measurement, my X is written like 17.615334 with sigma X as, so I repeated the experiment. I got my X value, the best X value is this, and I took the average, and my calculator is giving me this number. Similarly, I calculated using the definition of sigma X, and I am getting this number. And I know that my list count of the instrument can only take me up to 2 digits or 3 digits. Okay, so the error in the error is uncertain at the second decimal place. You can see, if I take out the last 3, okay, in the sigma X, the following digits have no meaning. So that means I should round it up respecting the list count and the insignificant digit. My sigma X should be rounded up to 0.23. So if I keep my sigma X as 0.23, X should be given to 3 decimal places. Okay, this has to be kept in mind. So if I am giving, let's say, 4 decimal places sigma X, and X is up to 3 decimal places, it will be wrong, because my uncertainties cannot be measured more precisely than the original measurement. That is why the number of decimal places are very, very important. And once you have decided that my sigma X should be measured up to 3 decimal places, I have to restrict 3 decimal places on X. Okay. So now let me put up the rule. A general rule of rounding off is the following. So let's say, so a general method of rounding off of the numbers is to take all digits to be rejected. So let's say you have decided that after 3 digits I will reject everything. So then put a decimal point in front of that. Then if the fraction which is formed is less than 0.5, then the less significant digit is kept as it is. I'll give an example, then that will be clear. So if you take this example here, so now I am putting a decimal point in front of the rejected digits, so that yields, if you look at the value of X, so I have to keep 3 digits, then I am putting a dot. So that dot is giving me 0.334, which is less than 0.5, right? So then my point number 1 tells me that rounding off result will be 17.615 and then plus minus 0.023, which was coming from sigma X. So I didn't do anything because your 0.334 is less than 0.5. So it is insignificant. Let me take a case where my x value had it been 17.615634. Now I am putting a point which is making 0.634. Okay. Now this is higher than 0.5. So then in that case, that 615, that 5 number will be increased 1, making x as 17.616. Then I put plus minus 0.023. So if the situation is then the case number 2, where it is 17.6155, for example, then I am putting a dot after 3 decimal places. So that is 0.5. And now 0.5 is not less than, it is equal to 0.5, right? So in that case, what is the rule? So rule is, if it is odd, if the preceding digit is odd, then it will be incremented by 1. So since the red digit 5 is odd, so I increased 5 to make it 6, and then my rounding off rule says if that is odd, then it is 17.616. In case of it is even, so for example, I have now changed that 5 to 6, which is red in color, so that is even. So in case of even, so you don't do anything, leave it like that. So these are actually the standard rules one has to, so no increment on the least significant digit. So these are actually rules for rounding up. And one more important point I should write is, rounding off in steps should be avoided. Meaning, you finish your calculations, at the end use the formula and all that, and once at the end you have the final result, then round off. If you do rounding up in each step, you will end up with big problem. So that is not allowed. Okay. So you can check that. So rounding up at the end and rounding up in each step. So what is the problem that you can check? Okay. So that was a small thing, but it is very essential while quoting our numbers. So now slowly let's go to weighted average. So weighted average, I have seen that it was a little bit introduced by Professor Kajari Majumdar yesterday, but I think I have a different approach of bringing it from the principle of maximum likelihood. So let's see if I can do the job. So the problem of combining separate measurements. So given that a physical quantity is measured several times and perhaps in separate laboratories, how to combine the measurements and to have a best single estimate, because you might have seen something is measured in different laboratories and you have to give the best measurement taking the average. If this kind of situations happen, or for example my old example of measuring acceleration due to gravity in your laboratory, if 5 students are measuring, each student is taking multiple measurements and giving you a number, that is his best number. If you have 100 students in the class and the teacher has to report to the principal, okay, my laboratory gives this answer, then of course you are going to take average on all the 100 students, because you do not know whose measurement is very good and you assume everybody has done the measurement cautiously. So in that case, let me take a simple example of 2 students, A and B. The measurement is the following. After multiple measurements, they report x is equal to xa with the uncertainty sigma a. Similarly, the student B. And then if the discrepancy, so first I have to see how discrepant A and B are. So what is discrepancy? Discrepancy is my xa minus xb. If that is too high compared to the individual errors, then the measurements are not consistent. So in the first go, I should suspect somebody is wrong. Okay. So how do I pictorially show that the measurements are not consistent? So now I am showing this here. You see, in the measurement on the left side, the discrepancy is 10, and in the y side measurement, the right hand side measurement, discrepancy is also 10. But if you see, the discrepancy on the left hand side is much higher compared to the individual errors which are shown in the vertical bar. And because of that, these two measurements are not overlapping with each other. But when you look at the right hand side, you will find even if the same discrepancy 10 is there, because of the larger uncertainties in their individual measurements, these 2 points are overlapping within the error bar. So the conclusion is, the first point what I have written here is very important. Your left hand side measurement is not acceptable because these two students, they are discrepant beyond their uncertainties, and the right hand side measurement is correct. So how many of you feel that, okay, if somebody is plotting or two people are plotting like this and it is bringing it to you for your judgment, which one you will accept? Initially, without doing an analysis, I think people will accept the left one because this is precise measurement. If the precision is better, but they are discrepant for whatever reasons. Okay, so now while taking the average, the right hand side becomes important, and the general rule, guiding rule is your discrepancy much greater than individual dispersions or the deviations. The measurements are not consistent, so you cannot take it for calculation. So now, while developing the theory of weighted average, let me assume that both the measurements are consistent, meaning your XA minus XB is not significantly larger than the individual errors sigma A and sigma B. What is the best estimate? X best of the true value? X on the two measurements. What is the possible guess? So possible guess, somebody will say, okay, these are only two entries. So let's average it. So just your arithmetic average, sigma XA plus XB by 2. But the caveat is, this is not correct if sigma A is not equal to sigma B. How can you give equal importance to two measurements which differ in their sensitivity, or one is accurate in the sense error is less, another is having more error? You cannot give equal weightage or equal emphasis to two measurements when the errors are different. So can I develop a theory giving proper weight depending upon the uncertainties in hand? Then if my weights are same or the errors are same, I will come back to my arithmetic average. So then that will be the master formula. And the answer is yes, it is doable. So let's develop that. So the average gives equal importance to both the measurements, whereas more precise reading should have been given more weightage. So that is what we believe, right? So now let's assume all systematic errors have been identified, all remaining errors are random. So we understand the error part. And the measurement of X are distributed normally around the true value capital X. So the weighted average, I use the principle of maximum likelihood and assume that both measurements are governed by the Gaussian distribution, and I denote X capital as the unknown true value of small x. Therefore, the probability of student A obtaining his particular value small xa is proportional to this Gaussian distribution. Okay, 1 over sigma A e to the power minus xa capital X square divided by 2 sigma A square. So similarly for student B, the similar formula I can write, and note that the subscript X indicates the probabilities which depend upon the unknown actual value. So the probability that A finds value xa and B finds value xb is essentially the joint probability which are multiplied, and this will be proportional to 1 over sigma A sigma B e to the power minus chi square by 2. And let me define my chi square, because this is just a multiplication of the right hand side, and that chi square, because of exponential, they will be added up, and I get minus e to the power minus chi square by 2, where my chi square is defined in this way. Okay, and chi square is essentially the deviation of my measurement xa from the true value capital X and weighted by the standard deviation of distribution for A. Okay, that is the definition of my chi square. And this problem using principle of maximum likelihood is equivalent to chi square minimization, the one we discussed last time. Okay, so now what is the best estimate of X is actually the value for which the actual observations XA and XB are most likely. So then joint probability should be maximum, and this brings up the chi-square minimization, because chi-square actually lies in e to the power minus, minus x square, minus of the exponent. So that is why this problem is equivalent to chi-square minimization, or it is also called as method of least squares, because as you can see, these are individual squares involved, okay, and this has to be least so that exponential term is less. And exponential term minus less means, so your probability is higher. So now there are several terminologies to digest, right? So maximum likelihood is the underlying principle to maximize the probability, and your chi-square minimization is again another terminology, and method of least square, because the least squares are least. So now I make D chi-square D capital X to be 0, then I solve it. The solution anyway you can do it, and you can follow from my video, so there is no point discussing on the arithmetic solution. And so here after solution, so you are getting this capital X with this formula, the last line formula. You have a look. So essentially it is in the denominator you have 1 over sigma a square plus sigma b square and all that. Okay. So now let's define my omega a is equal to 1 over sigma a square, omega b is 1 over sigma b square. Okay. These are actually weights. So once I define these weights, and you can see if sigma a is higher than sigma b, my weight for a is less and weight for b is high. And that is what is expected. More precise measurements should get more weight, right? So that is what is mathematically taken care of. Now my best estimate for x is x weighted average, which is equal to omega a xa plus omega b xb divided by omega a x omega b. Have we seen this kind of formula earlier? Can anybody point out? Till I am taking a sip of water. Have we seen this kind of formula anywhere earlier? Yeah, this Microsoft Teams setup is such that I cannot see anyone. How many people are there? I cannot see also. But anyway, hope you are listening to me.
Maybe center of mass.
Correct. Okay. So maybe when you interact with us, you can just tell your name and where are you from. So that although we cannot see you, that will give you us a feeling. If many people are from different parts of India.
Yes, so, sure, sir.
Yeah.
I am Nanath Khobrekar. I am a first year student on MSc program, currently enrolled in IIT Bhilai.
IIT Bhilai, great. Okay, good. Okay, so you are absolutely right. So that is actually the formula for weighted average, and it is equivalent to what we learned from center of mass. Okay. So now let's discuss analyze a little more on this x weighted average. So if my sigma a is equal to sigma b, this is giving equal weight omega a and omega b, and I am getting back my simple arithmetic average, right? That is what I promised to start with, that more precise measurement should be given more weight, and my master formula should take me back to my simple average, giving equal weightage when I do not care about the precision, right? So my point number 1 is actually confirming me that my master formula is correct and my earlier conventional knowledge is proved to be correct. Okay, arithmetic average could be, we could get back. So this actually just tells me that it's a reductionism. For example, correspondence principle, suppose you are in a relativistic domain, you cannot say my classical mechanics is wrong. Rather, you should make a correspondence that in the low velocity regime, so you should get back to your classical knowledge or classical mechanics. Exactly similar way, although I gave you a master formula, I made a correspondence to my known arithmetic formula. That is what is very important. Okay. And if my sigma A is not equal to sigma B, so weighted average is not equal to the ordinary average. And as somebody told from IIT Billai, this is exactly equivalent to the center of gravity formula of two bodies, and we are accustomed with this. And yeah. So now the question is, can I generalize this? Answer is yes. You can go for 100 students, 200 students giving your measurement, and I should have a generalized formula. So now in the generalized formula, I generalize to xn, corresponding uncertainty is up to sigma n, and I could write the formula. It's simple summation I is equal to 1 to n of omega I xi divided by sum over of omega I, and this is the number for your mean value, right? Because you have taken the average, and there is something called error on mean. What about that? So you have to also find out what is your sigma weighted average. Okay, so now these omegas are essentially related to sigma as square root of inverse of the square root. Okay, and with this we are in a position now to write the uncertainty in the x weighted average, and that is equal to 1 over of square root of summation of over I omega I. Okay, and you can also prove this thing, and the final expression for weighted average, the prescription we followed, so that should give me that, this master formula. I don't want to read it out. Okay, so this is the formula for weighted average. It may look very complicated, but that actually gives back my ordinary average, and this also respects the error propagation formula. It also respects the statistics and everything. Okay, so that's the reason this is very powerful formula, and I would give you a homework that use the error propagation formula, which I am going to teach you or discuss with you today, and derive that sigma weighted average, which I have written by hand like this, should be equal to square root of sum over I omega I. Okay, so you can actually show this thing with the propagation of errors. Let me take one example. So, for example, there are three measurements of resistance, and the resistance in the unit of ohms by different students are given like this, and the corresponding uncertainties you can see sigma 1, sigma 2, sigma 3, and from these 1, 1 and 3, which are the sigmas, I can calculate what are the weights, and Wi are my weights, which are going like 1 over sigma I square. So from this, so I have omega 1 or W1, W2, W3, and you will find the weight is 1 over 9 for a less precise measurement, which is the student 3. So automatically that is taken care of. And if you go to the master formula, so that resistance of weighted average is given by that formula, which is 11.42 ohm. So the uncertainty in this answer will be omega weighted average, and that formula you use, and you will get 0.69. Okay, and then possibly depending upon your instrument, so you can round it up to a single digit. So if I round it the error first, so that is 0.7, because 0.69 can be rounded up to 0.7, and then your first term, if you round it off, or weighted average 11.42 should be rounded up to 11.4 following the rounding of rule which I discussed. So you see, that is the reason I discussed rounding of rule, because I know that I am going to encounter this kind of things. Okay, so different student measurements, how you express at the end. Okay, so now you have a flavor that our final conclusion on the resistance measurement should be R is equal to 11.4 plus minus 0.7. And you see, the many rules we have followed here up to here. And when you write a paper, your research paper, or in the laboratory note, so you will find that all these things will be highly useful. Okay, so I thought of discussing about the rejection of data, which is important. I do not know the way I am going. Almost I am 1 hour behind, looks like. But fine. So let me discuss about the rejection of data. and I will again take one example to show which data we should suspect like it is anomalous. Let me put up the theory first. There is something called Chauvinet's criteria. So let's say we have n measurements, x1, x2 up to xn of a single quantity x, and from all n measurements we calculate my x average and sigma x. If one of the measurements, say x suspect, differs from the average value so much that it looks suspicious, then once I put up my theory in the example, this will be clearer. So hold on for some time. So I have a set of measurements. I calculate my x average. Then I give my dispersion or my spread sigma x. Somewhere I try to suspect somebody's measurement because one of the measurements is highly away from the average measurement. Okay. Of course, if it is acceleration due to gravity, the standard number is known to me, and anything highly suspicious, I may say, okay, you are wrong. But that may not be the case always. Always known things cannot be measured. Okay, so sometimes you have to suspect one of the entries. So then let me say that x suspect is that entry which I am suspecting. Then I calculate the deviation x suspect minus x average. I found out how much standard deviations it is away. So that gives me t suspect. Essentially, t suspect multiplied by sigma x tells me how many standard deviations your suspect is away from the mean value. Now one finds the probability of outside of t suspect. So this is exactly equivalent to the earlier problem I told you. And that a legitimate measurement would differ from x bar by the amount which is t suspect or more standard deviations. Finally, multiplying n, because statistics plays a role, so you have to come back to the number n, okay, because that affects your x average and sigma x. So multiplying with the number n, the criteria says that the total number of measurements will give you small n, which is expected number of deviant as x suspect, that is your n multiplied by probability outside this t suspect. And if you found that your expected number is less than 0.5 or 1/2, then as per this criteria, one should reject this x suspect. Don't count or don't take x suspect and recalculate. Take out that entry and recalculate the x average and sigma x using the remaining data. Okay, so this is a prescribed procedure. If you suspect any statistical data, so first you have to establish with some criteria, okay, so this is one anomalous entry. So let me take one example to prove this or to justify this. Let's say somebody, a student makes 10 measurements of the length, and we found with the same scale, and we found these are the entries, 10 measurements. And then we go on calculating x average and sigma x, which we are finding respectively 45.8 and 5.1. Okay, and looking into the average, which is 45.8, I started suspecting 58 could be one anomalous entry. Okay, and any anomalous entry can actually make big perturbations in the dynamics of the system. So I suspected I suspected 58 entry, and I write that is my x suspect, and that is 2.4 sigma away from my x average. So my t suspect is 2.4. So now I calculate using Chauvinet's criteria. So what I do is probability outside 2.4 sigma is essentially, since I am calculating outside, so it is 1 minus 1 is the total probability minus the probability within 2.4 sigma, and this probability within 2.4 sigma is I can get from the table given in the statistical table given in any of the books. So that will give me this number 0.984, and then finally I am getting the number 0.016. Okay, and as 10 measurements are there, so I have to multiply with this, and finally I found that 10 multiplied by 0.016 will give me 0.16, and 0.16 is less than 0.5. Okay, And because of this, he should at least consider rejecting the results. Don't count 58. So let us see if, as per this criteria, I could prove that 58 is an anomalous number. I go on recalculating my x average and sigma x, okay, and x average is now found to be, after taking out 58, it is 44.4. You see 45.8 and earlier x average and new x average, there is no big difference. But if you look at sigma x after taking out 58, now earlier it was 5.1, now it is 2.9. So 2.9 sigma is much better compared to 5.1. So essentially these kind of anomalous entries will create bigger dispersion or bigger uncertainty in the measurement. So that is why if you start suspecting a data, so this is the prescribed procedure of rejecting the data. Okay. So I hope with this prescription it is clear. And for this actually you can have a look at, after my class, if you want to know a little more. So you can look into John Taylor's book on error analysis.
Sir.
Yeah. Who is this?
Sir, suppose
name and place, that is always better.
What's sir? Sorry, sir.
I requested that when you speak, you just tell your name and from which institute you are from. So
Okay, sir. Yes, sir. I am Tanmay Verma, MSc first year student here at NITJ Jalandhar.
Great.
Go ahead. Yeah, sir. I want to know that can we use this approach while determining an orbit of any celestial object? Like there could be some point where we can get a distance which would not match our observations.
You see, here while discussing about the criteria, I have not brought in any discussion of the physical system. Okay. So what I am saying is, it is purely related to any sample of data you have taken from any physical system. Okay. So there, if you found that one of the entries is highly deviant from the average and you started suspecting this number could be anomalous because of certain reasons, so then you put up this criteria and see if it is allowed number or no, and then you rule out and do the averaging again. So this is independent of any physical system. Okay, it is for any sample. Okay, for example, you are measuring acceleration due to gravity, my favorite problem in the laboratory. In your tabletop experiment in the lab, you have separate different entries. You are taking the average, okay, and you have to report to your teacher. So there, if you find something is very anomalous, that will affect your spread also. So then you should rule out, just not like that I put a cross and I don't take it, but the scientific way of dealing with this anomalous data is this. Okay, so it is independent of any physical measurement.
Yes, sir, got it.
Thank you. Okay, so next is a natural gap, but I don't know if I should proceed or no. So next actually I am going to discuss about error propagation, which is combination of errors. So here I must tell you, I think I should another 15 minutes we can go ahead, because in one more class we should finish all the discussions, what I intended to. So a word of caution is, don't get confused with the word error or uncertainty. Error is not a mistake. In statistical language, error is not a mistake. So now this typical picture which is shown on the front page of John Taylor's book. So you will find that there is a train accident. This is a steamer, okay, it's a steam engine train. So this, I take a book and what I do is I start reading the book. But sometimes it is worth seeing why the picture of the book is like this. So this is very fascinating, this particular book cover, and also the back of the cover is actually John Taylor is lying on a bed of thorns, spikes. So that is also telling you some physics. It's a beautiful book, have a look, and front page is like this. So this shows a disastrous error. Again, quote unquote, I am saying error. It's not a mistake, but it is your improper way of estimating, that is uncertainty, okay, occurred on 22 October 1895 at the Gare Montparnasse in Paris, when the French TGV is the high-speed train of France, that is called Trans Grande Velocité, okay, arriving from Granville in Normandy, okay, Normandy is in your English Channel, north of France, failed to stop in the station as planned. So, if anybody has seen Gare de Montparnasse, that station name in Paris, Paris has many stations. So, fortunately, I have visited all the stations almost in Paris. So, that is a full stop. Full stop in the sense, anyway, Paris, almost big stops are actually full stops. Like you might have seen the stations like Howrah. So, the train has to make a full stop. You cannot go in the same track. You have to change the engine, change the direction. So, in a similar way, you will find in Montparnasse station, it is a full stop. So, the driver of this engine has to estimate, if I put a brake, so the distance is this much, it is not automated that time, and the train has to stop. So, there was a estimation error for which this accident was there. And this train, I am happy to say, because the train was coming from Normandy, Granville, and this Montparnasse in Paris. I have seen both those stations. That is why I am quite happy to put up this picture for you. Yeah, so Normandy and Montparnasse, I have seen both, and it is very fascinating to see the station and this particular accident as a measure of uncertainty. Okay, so with this, let's enter to the domain of error propagation. So, what is the necessity of propagating the errors? So, because you make some fundamental measurements like length, height, area is not a measurement, it is a calculation, right? So, after measuring length and height, so you go back and calculate the area, meaning there are derived quantities which depend upon independent measurements, okay, and the independent measurements are having uncertainties which should be propagated to the derived quantity. So, that is the meaning of error propagation. It may be very, you may say, okay, it is easy, but it is not easy job. Error handling in experimental physics is a very difficult job. So, your normal measurement in high energy nuclear physics, the amount of time it takes, the measurement of error takes more than that. Okay, so that is the reason is each of the schools in high energy physics, this error propagation is taught again, and again, so that you do not forget it. Okay, so it is very simple, but okay, so it is a highly difficult task to that depends upon the problem in hand. And correlation and randomness of variables are also important. You should understand the variables you are measuring, and the competition between the systematic and statistical errors is also important. Okay, and those statistical systematic uncertainties I have told you earlier. And I would like to bring up a proverb or quotation here by William Blake, that errors of a wise man can make your rule rather than the perfections of a fool. So you have to digest this sentence. Okay, if a wise man finds an error, so that becomes a rule for others, and this is compared with the perfections of a fool. Okay, so this slide I would like to skip, because I discussed last time how that n-1 factor is coming, and yeah, so this I would like to skip, because I discussed this that factor, that factor 1 over n-1, which I brought in the last class. So that is discussed already. So this is the recommended formula to calculate variance for a finite sample that we had discussion in the morning. Okay. Yeah, for a finite sample like this, so actually you should consider taking this modified formula which takes care of the finite sampling effect. Okay, so this we discussed, and this is just one example, so I can skip this. Okay, I think this is a natural break, because I am also getting tired. It's a natural break to stop here, and next class I have enough material now. I can go ahead with the count rate determination and their error in the counting experiments, like experiments which follow Poissonian distributions like radioactive decay. So I think it is a good point to stop here. And next class tomorrow early morning for me is 6:30. So I will start counting experiment errors, and slowly I migrate to error propagation and error ellipse and other things. And then we discuss briefly about least square. I think whatever assigned job to me, I can finish easily tomorrow with little extended class. But yeah, I would like to stop here.
Thank you so much, sir, for this informative talk. Now I would like to request the audience if anyone want to ask any question. So they can turn on their mic and ask.
Hello, sir.
Yeah, please go ahead.
I'm Chandra Kumar from RV College of Engineering, Bangalore, sir.
Okay.
Thanks for the question. And just a small query. You mentioned about Chauvinet's criteria. So, is it can it be mentioned in a research article also that this method was followed?
So that is actually, yeah, so that is part of the data cleanup. Okay. So in the research article, you can actually write that following this criteria, so anomalous events or entries are taken out. Absolutely right.
Okay, yeah. Thank you very much, sir.
Yeah. Any other question?
Sir, one more query. What should be the minimal number of samples? Because there will be some limitations in, as you said, in physical measurements. Is there a thumb rule?
There is no thumb rule. That depends upon what you are looking at. The physical problem in hand will decide that. Okay. So, for example, once actually you go ahead with your physics problem, that will actually decide what is the statistics necessary. Okay. For example, if your statistical error at the end of the day on your signal is too high, so then your statistics has to be increased. So it depends upon the physical problem in hand.
Okay, sir. Thank you.
Yeah, no thumb rule for this.
Any other question from the participants?
So just out of curiosity, how many participants are there? I cannot see the number.
Sir, at this time, 133, 135, around 135.
Good. It's
Right,
a good number, and it is nice to note that the whole our motherland is covered, starting from Jalandhar to Bangalore.
Yeah,
So, that is very good.
that is.
Yeah. Okay, so if if additional questions are coming, please feel free to interact more tomorrow morning. Okay, so tomorrow morning maybe we'll resume again. Fine.
Yes.
Yeah.
Tomorrow morning at 11 a.m. the third talk will be by Professor Raghunath Sahu. Okay,
Yeah. So your time 11 and my time early morning 6.
Yes. 6:30. Yes.
Yeah. Okay.
Thank you, sir.
Yeah. Thanks a lot. I interacted, I enjoyed with beautiful questions, and good that people are trying to understand. Of course, a few things will be new for the general domain. And I urge that the students who are in high energy physics or nuclear physics dealing with large number of huge volume of data and many variables particularly. So my next class would be quite useful for them. Okay, because I will go from single variable to a multivariate analysis of errors, and then give a general prescription of error matrix and transformation to error ellipse and all that.
Actually, there are the participants from high energy physics, I think, who have joined.
Sir, can you please show the repeated measurement slide once again?
Repeated measurement slide, yeah, why not? So you can see my screen, right? I have not taken out. Yeah, this one?
Yes.
Or this one?
Yes, no, this one.
Okay. This part of the discussion is from Roger Barlow. Okay, so if you have any question, you can ask me, or I would say that go through Barlow once, and because once you read and digest, things will be much clearer. So you can follow this part from Barlow. But go ahead, asking questions. Yeah. So.
Sir, next slide. Slide number 8, not 7.
Okay. Fine.
Yes, ma'am. Go ahead, ask your question.
You wanted a snapshot of the slide, or you have a question?
Yes, snapshot of this.
Okay. Fine.
Yeah, sir, there is a question regarding this slide. Has also raised her hand. We like go ahead, please go ahead, Deepika, and ask your question.
Sir, I have a question regarding the rounding off of errors, sir.
Okay.
So if I am considering a data which consists of different significant digits in different different data points with the different significant digits in it. So if I am analyzing the data and in the result, what should be the number of significant digits that I should consider?
You see, people usually take 3 significant digits. Otherwise, you see, I do not have any instrument which can actually give 1,000 times 3 significant digits after the decimal point means it is 1,000 plus, right?
Yes.
So 1,000 divisions. Let's say I am measuring time, and ultimately I am writing minutes. So my watch cannot give 1/1,000 minutes, right?
Yes.
So when I quote, simply my watch determines what is the list count of this watch, and if I write my sigma x is 1/1000 of 1 minute, so then any person from the audience will say, how did you measure that? Right? So that actually decides how many digits I should put it.
Okay.
Okay, for example, if I take a scale, 1 millimeter is my list count, and I am putting my error up to 3rd digit. So that is telling me that it is 1/10 of the millimeter I am measuring, but my scale cannot do that.
Yes.
Right. So if anybody is smart enough, superficially seeing and scientifically observing is different, right? Yes. So if scientifically we are evaluating, so then immediate question will be something is wrong because you are quoting something below your list count.
Okay.
Okay. This reminds me a beautiful story. In my BSc, I was evaluated in BSc physics. Some magnetic experiment was there in the exam, and I had taken beautiful readings. And the external comes and he says, "Can you take one reading in presence of me? Your readings looks quite beautiful." So then I started taking the reading, and I could not get back any of my readings. I could not reproduce my results. So then the external started saying, so something is wrong. You cannot do your experiment. Okay. So then I started thinking, I remember that. And I told the external, are you carrying any magnetic object in your pocket? Or maybe one piece of bar magnet? Then you may not believe, I remember that event. So the external told, you are absolutely right. You should get the highest mark because I have a bar magnet in my pocket. Okay, so this is called my observation, his observation also. But I should give equal credit to my teacher, external. So you see, going scientifically has a different value. And that single question cleared to me, in the sense I have understood the experiment. Okay. And I also urge all of us, all the teachers in the game, if any number of digits, particularly a student is quoting, so we should actually educate them by saying, how did you measure up to 3 decimal places, 4 decimal places, where as your instrument list count is this. Okay. So once you guide a student in this way, I think he will not forget in his life. Okay, thank you.
Sir,
Yeah.
sir, we have two instruments. One list count is 2 digit, another is 4 digit, and we are try to find the function of combination of these two instruments. What will be the list count then?
So we have to respect the higher one, right? If you combine, for example, one instrument measurement you are giving, so that can go up to 4 digits, right? And second instrument can go up to 2 digits because the precision is less. Now your job is to combine these two results, right?
Yes, sir.
So then you have to respect the lower precision because it has the inability, it cannot go to third digit, fourth digit. Okay, and while combining like this, you have to give respect to the higher error, and yeah, so higher error means less precision. That is what I told you.
Okay, sir.
Okay, yeah, because error has to be always higher error has to be quoted. You cannot hide the errors. And similar concept applies to statistical versus systematic errors. If systematic errors are higher, so higher has to be quoted. Always error higher will be quoted.
Okay, sir. Thank you, sir.
Any other
Sir.
further questions? Yeah, please go ahead.
Hello, sir.
Once again,
Yeah,
I have
yeah. Just tell your name and institute.
I am from IBM, Institute of Business Management in Jadavpur.
Okay. Jadavpur ka, okay. West Bengal.
Yes, West Bengal.
Yeah.
I have taken a screenshot on slide number 8.
You have taken, fine. Or you want to take?
Yes,
Take it.
I take.
Fine.
So, Somek, do you have a question or you just?
Hello, sir. I am Sunil from NIT Tiruchirappalli.
I take the screenshot.
NIT Trichy. Yeah, please go ahead.
Yes, sir. My question is, sir, what are the tools we are going to use for this statistical data analytics?
What are the tools means? You mean softwares?
Yes, sir.
I see the software is dependent on different areas of science. For example, if you look at condensed matter physics, they use some pre-built Origin, XM Grace, XMGR, many different plotting softwares. And in high energy physics, we write our own C++ root-based softwares. So softwares for data analysis is completely dependent on the areas of physics or any branch of science, whatever they are using. But more often people use it like a black box, thinking that the libraries and fitting programs are perfect. But I would say if you have little more understanding, so then your data analysis will be much better. For example, use it as it is because those are standardized softwares. And along with that, try to understand how those things might have been implemented. For example, the ones we are discussing, the fitting procedure, chi-square minimization, because somebody has written those programs after understanding whatever we are learning today and implementing them properly. And somebody might have certified that the program is correct. Otherwise, we don't use blindfoldedly, right? Yeah.
Okay, sir. Thank you so much.
Good, nice that people are from many different states. It's nice to see. So it would have been nice to see all of them in the campus of NIT Jalandhar. So at least tea time we would have enjoyed. No, we are missing all these things. Okay.
Yeah, that would have been great. So, are there any further questions for Professor Saab?
NIT Jalandhar is due whenever things get normal.
I am looking forward to. So I go back maybe the coming March I go back. So then I am looking forward to. Yeah. Thank you.
Hello? Question, sir? Hello?
We can hear.
Yes, sir. In some paper they put average error. Average error means
we can add all the errors and divided by number of the data. It is better than give average error.
Average error.
Average error percentage.
While presenting, your question is giving average error.
Average, yes, yes.
But I guess we discussed about the error coming from the whole data sample and how statistics affects that. So if your number is, if your quoted number is mu, so then error on the mu is your sigma divided by square root of n. So that takes care of the statistics effect of n, and sigma is coming from the average of that spread. Yeah.
Okay.
You want to give the lecture? No? Okay.
Yeah, Jishan is Ansari. Do you have any question? You have raised the hand.
Sir, am I audible?
Yeah. Go ahead.
Sir, can you please name one open source software for such statistical analysis?
Open source, the one we are using is root. Okay, root.solve.ch. So if you go to root.solve.ch, that is C++ based software. You have to write your own analysis code, but all libraries and everything are available open source. Okay, so that is what we people use it. And which branch of science you are from?
Sir, I am from mechanical engineering, IIT Goa.
Mechanical engineering, I have no idea what software they use. But there, okay, so that AutoCAD something, so that is for your drawing purpose, I guess. But this data analysis software, I do not know. But if you are accustomed with C++, you can start using root. Otherwise, Origin is a good software. Many people use in material science and condensed matter physics. Yeah, Origin is a good software. But that is not open source. You have to pay for that.
Yeah, and may I add something to this as well? You can use any of the Python-based softwares, like Jupyter Notebook has some of the features like Panda libraries and Matplotlib. So they all have those statistical features built in it.
Right.
So we can try to scroll that a bit. Means.
And you have to know Python, I guess, right?
Yes, sir. Sir, R, we can use R also. There is one package name.
There are many, in fact, there are many, but if you want to use like a black box, for example, Origin software, so you load your data file, then try to interactively plot, so those things are doable. But root is not interactively, you have to write your own C++ program to plot it. Okay, so like loading your data file and analyzing the spectra is available in some of the softwares. But the one we are using for high energy physics, which is root, you have to write your own program. It's different. So it is C++ based software. It has, for example, its own random number generator and everything. But how to call that random number generator, you have to write your own program. So that is what I meant.
Thank you, sir.
Okay, you are welcome.
So maybe probably with that, I think we should try to conclude. Actually, thank you so much for giving. We have taken a lot of time, right, from your side. Thank you so much. And I probably in the morning it have been quite early for you, right? 6:30.
Yeah, it is 6:30 and 6:30. Everybody is sleeping, so so it is quite early. But then I thought I can finish this and I can go to my office. So in that way, that is good.
Okay. Yeah. Thank you so much. Thanks. Thanks a lot. Okay. So then.
Okay. So see you tomorrow morning. Yeah.
Okay. Thank you so much. Thanks.
Yeah.
Thank you, sir.
Okay, so bye for now. Bye, all of you. Good evening.
Bye. Yeah. Thank you, sir. Thank you so much.
Thank you, sir.
And a big thanks to all the participants as well for staying till the end. See you people tomorrow morning, 11 a.m. sharp. And the request is that please try to connect maybe at least 5 minutes earlier right? So that we can get started on time. Okay, thank you very much.